If you've managed to stay with me this far, congratulations! You finally got to the part where I speak of airships themselves. Since it's the feature that drew me to Opel's story in the first place, before I got caught up in the characters and the world, it seems fair that I should convey some real-life knowledge and perspective about how airships work, past, present, and maybe future. It also might be useful to compare how the real technology works versus how it's presented in fiction to help appreciate the divide. Because what we don't know about the potential of airship technology is thus deprived us. And I think we could use some more of that wondrous realm of flight. Airships are in a class of aircraft called aerostats that derive their lift from buoyancy using gases such as hot air, steam, or lifting gas. This is opposed to aerodynes that derive their lift from wings moving through the air, fixed-wing airplanes, rotary-wing helicopters, and flapping-wing ornithopters as such. Airships are a development of balloons that use lifting gas in gas envelopes and ballast to control their weight mid-air, with the addition of onboard propulsion and aerodynamic steering, so they are not driven by the wind. Lift is produced by the difference in density for a given gas at the same pressure as the atmosphere. If the lifting gas used is either hot air or steam, fuel must be burned to maintain heat and the low density needed for lift. Hydrogen and helium are themselves naturally less dense and thus lighter than air without heating, although heating can be used. Hydrogen provides about 71 pounds of lift per 1,000 cubic feet. Helium, by comparison, provides about 61 pounds of lift per 1,000 cubic feet in standard atmosphere. Of course, the atmosphere is hardly ever standard, alas, that's a subject for later. Suffice to say, the in-story hydrium is purely fictional, granting greater lifting capacity than hydrogen, but extracted from underground deposits like helium. The only real-life gas with greater lift capacity than hydrogen gas would be a partial or total vacuum. Nothing else comes close to that while still using a fabric envelope. Even today, the structure needed to contain a vacuum would be too heavy to benefit from the extra lift. Ballast is crucial for balancing the lifting capacity of the onboard gas with the rest of the aerostat's weight, without which the ascent may be uncontrollable or the descent unstoppable. The weight of the airship changes throughout the flight, even throughout a single day, so ballast is taken on expressly for when it is needed to balance the airship's weight with the changing conditions. Such conditions include fuel being burned, reducing weight, or gas being released, or leaking, reducing lift, and atmospheric changes that also change lift, or weather that can add weight to an airship. Ballast can be bags of dirt, such that was used by balloonists, or water as used by airships both in story and in the real history of airships during the early 20th century. Future ballast technologies may include the ability to compress and store lifting gas in superpressure balloons within the airship envelope, reducing lift when needed and saving the gas for later use. The structure of an airship needs to hold everything from the envelope, the outer skin, the crew, passenger, and cargo accommodations, as well as support the weight and thrust of the engines providing propulsion. Believe it or not, the earliest structures for rigid and semi-rigid airships were wooden, before airships used aluminum and the particular alloy duralumin for stronger and lighter structures. The in-story mentioned alum-iron is entirely fictitious. The closest real substance is called iron aluminide, a mixture of iron with 18% aluminum by weight, that, while almost as strong as some steels, is not nearly as light as aluminum alloys. Additionally, it's not ductile at room temperature, so it cannot take a load and remain unbroken. And water reacts with the aluminum in the alloy to produce hydrogen, which turns the iron itself brittle. It would be a terrible material for structures of any kind. In contrast, the use of lightweight alloy and composite materials are a better choice for modern and future airships. The structure of an airship also includes the particular material used to contain the lifting gas in the envelopes. The in-story mentioned gold beater's skin, which is the intestinal lining of cows, is very much real for our early 20th century airships. Of course, producing any large number of airships would be bottlenecked by the supply of cows not needed for milk or meat, so we moved on to better and more common gas-sealing materials, such as rubberized cotton. Depending on whether an airship is either non-rigid, semi-rigid, or rigid, the outer skin is either combined with the gas-tight envelopes or separate, respectively. In fact, in story, the skin of the Aurora is referred to as cotton, but made waterproof and fireproof, without further details. In either case, the outer skin has to be protected from the wind, water, cold, and heat that would degrade the textiles, and in turn protect the lifting gas envelopes within. The technology level seen in story, while not specified, portrays a setup where the outer skin is coated to be reflective of sunlight, which keeps the inner envelopes from absorbing or expelling too much heat throughout the day. In real-life airships, this was achieved with fabric coated with layers of cellulose acetate butyrate and metal powder, often aluminum or iron oxide. Real-life modern airships have advanced the science towards using a variety of polymers in specific ordered layers to provide both envelope support, weather durability, and gas tightness. Finally, the propulsion in combination with aerodynamic controls is what gives an airship its freedom to fly independent of the wind. Both in real life and in story, internal combustion engines drive air propellers to give thrust, and with airspeed provide steerage for in-flight control. The only real difference is that in story, most of the relevant details about the engine's abilities are completely glossed over in favor of less technical aspects. Just like in real life, for airships, the important features of the engines are not just the propulsive power, but also their long-duration efficiency, their ability to reverse thrust, and what was very important in real life, the ability to recover water from the engine exhaust to make up for the lost weight of the liquid fuel. In story, the fuel is referred to as Aruba fuel, which is likely based on real fuel refined from oil. In story, Matt's view and knowledge of the engines is mostly incomplete, as fully comprehending them would require acknowledging the complicated array of subsystems needed to operate the engines: air and fuel intake, ignition systems, cooling, exhaust, and not just the noise but also the fumes, high temperature, and high voltage that could be dangerous. Thankfully, the adventure didn't require a detailed knowledge of the engines. Controlling the airship Aurora comes with a unique twist on the typical 1920s-30s era design. It's the inclusion of an auxiliary bridge in the tail section. Unlike what was attempted in real life, placing a bridge for controlling airship flight in the stern area has some advantages. When aerodynamic controls are moved mechanically by wheels and cables, the distance between them is shorter, saving weight. When flying at low level, the stern position helps keep the bottom side of the airship and the surface below in view. And when fine control for the airship is needed close to the ground or obstacles, keeping watch at the stern helps avoid collisions that you would risk if you didn't have a feel for vessel length relative to the confined space. Of course, operating an airship is more than understanding the science and mechanics of the technology. It requires infrastructure and standardized operating procedures with which to handle the airship when it's being maintained, prepared for flight, or even being recovered thereafter. Since airships have to be launched into the air, they always eventually have to be handled such that they can take off in manageable conditions. Before that point, an airship has to be secured such that it can be loaded and weighted for the conditions of the flight and the mission at hand. This would be easiest to do without the influence of the unpredictable wind. In real-life history and in story, this is done inside large hangars, which does the trick. However, in the future, since some airship operations may be confined to the outdoors, it would be a good idea to include a kind of windbreak that disrupts the wind before it buffets an airship around. Just like a breakwater that protects ships on the water inside harbors and ports from excess waves, a windbreak would protect airships and balloons from irregular and excess winds, at least up to a point, so that mooring and docking operations can more easily handle the airships. I have yet to see any description of such devices in stories or real life yet, but not for lack of feasibility. We certainly have the technology to uphold nets to dampen and diffuse wind close to the ground. Before every flight, for anything that flies, weighing what to take on is of paramount importance. For airships, it's especially important as it also concerns how much lifting gas and ballast is available for in-flight adjustment. While on the ground, the flight crew has to decide if they want to fully inflate the ship for maximum lift, to balance it with maximum payload, and make adjustments as conditions change in flight using thrust or aerodynamics, or if they want only partial inflation, such as to increase their potential pressure height. Unless an airship technology is used to recover lift or ballast lost through venting, deciding on the ground before flight is crucial to make the journey safely. It's also the time to adjust flight expectations for the forecast weather on the route during the trip. Imagine, if you will, that some part of the route will experience such low-density atmosphere that the full inflation of the airship won't carry the vessel and payload above the ground. So the flight is grounded at that point until conditions improve. It's the same with airplanes, such that when air temperature is too high and the density too low, it can be impossible for an airplane to take off because engines produce less thrust and wings less lift in lower density air. This actually brings up an important point about how the properties of lifting gas affect the ability of airships to fly and thus how they are designed. Remember how I pointed out in standard atmospheric conditions, hydrogen and helium produce 71 and 61 pounds of lift per 1,000 cubic feet? The difference may not seem so great, but for a given weight of air that's displaced, compared to the weight of the airship that works without its payload, the difference in lifting ability makes a big difference in the amount of payload that can be carried. For example, for the same airship that can use either hydrogen or helium with nothing else changed, using helium will correspond to a drastic decrease in payload, depending on how heavy the vessel is relative to the weight of air displaced. To carry the same payload, the helium airship will need to be lighter for the same size or much larger to displace more air to make up for less lift. In story, the Aurora's crew doesn't have to worry about losing lift by changing between hydrogen and helium because the fictional hydrium outlifts both. The next concern comes from the economics of producing it and replacing it after venting in flight. In these regards, hydrium shares the same production and replacement dynamic as helium. It is extracted from the ground and, once vented, is lost to the sky, diffusing upward to the edge of space where it can't be recovered. However costly that makes hydrium in universe, in real life it makes helium very expensive, such that even the smallest helium blimps have to find ways to avoid venting it whenever possible. In comparison, hydrogen, while also easily lost, is just as easily replaceable. There are several methods for making hydrogen, including electrolysis with water and steam reformation with petrochemicals that would make hydrogen far easier to produce that aren't limited to known underground deposits. There have been actual proposals for airships that use helium for lift, but also incorporated envelopes of hydrogen specifically as a kind of anti-ballast that helps avoid venting the precious helium. It was never implemented in any past airships, but it may yet be used in future ones. As for handling an airship in flight, The most fundamental skill an airship crew would have to know is how to control a balloon's weight. Balancing lifting capacity against ballast in the midst of the atmosphere and its changing air density and wind conditions. This is roughly parallel to boat and ship crews learning how to handle loading and steering smaller boats on the water. Which is funny that in story, the Aurora's crew act like there's a great distinction between their handling of their airship and how balloonists handle their craft. I got the impression that in universe, the flying of airships is treated more like sailing than the operation of powered transport. There's more said of the ship's rigging than of the airship's inflation ratio to the atmosphere's local air density. Of course, real airship crews have to remember the basics of ballooning in order to properly and safely manage flying their airship. They have to manage how inflated the lift gas envelopes are in given air density and temperature, and manage how much ballast is needed against the need for easier steerage against wind conditions and their static heaviness. Contrary to the portrayal in story, it's actually very hard to get the lift of the gas to exactly equal the weight of the vessel for very long. Crews compensate for the difference by tilting the airship to produce lift in forward flight. The airship is either pitched up when heavy or down when light. Or with more advanced propulsion, such as real-life vectored thrust propellers, they tilt the direction of thrust to make up the difference. And despite the Aurora's crews looking down on heavier-than aircraft in general, the principles of aerodynamics are just as important to flying airships as well. Without the dimensions and proportions of wings available on airships, what they have to work with are the cylindrical body and the tail surfaces, which behave differently in pitch and turning. If vectored thrust or side or vertical thrusters are not used, then knowing how the airship behaves when pitched or turned against the incoming air is vital for handling. Imagine, if you will, an airship that's heavy. It weighs more than the lift of the onboard gas. If you kept the airship physically level, then the airship would descend. If you wanted to maintain altitude, you would need to pitch the airship up to increase lift from the body, but at the cost of extra drag. Imagine the inverse: the airship is light, and if you held the airship level, it would ascend. This isn't always preferred, so as to stop ascending, you'd have to pitch the airship down to increase lift downward, at the cost of extra drag. Pitching up and down to make up for an airship's static heaviness is part of trimming the vessel for flight, and needs to be monitored and maintained depending on flight conditions and what maneuvers are required. This is especially important when an airship is coming to a landing. Depending on whether lift or weight is in excess, those are the times when an airship needs to maintain a certain airspeed to have the control needed to trim the airship until the time comes to dump the excess lift or weight and hopefully make a landing without a long runway, as it were. Without fine control of lift and weight during the flight, making a vertical landing would be exceptionally difficult if a crew had to rely on aerodynamic control alone. It's a major reason why, in real life, modern and proposed future airships often include vectored thrust and more airfoil-shaped bodies to make up for airship heaviness or lightness during the flight and upon landing. When venting expensive helium is not an economic option, vectored thrust and aerodynamic airplane-like landings are more viable than the imagined gentle docking of an airship from hover or vertical descent. Personally, it's a shame we don't have airship technology that operates closer to the fantasy we imagine, because with the right design and professionalism, it always seems technically feasible to have a flying vessel upon which we can embark on our own airborne adventures.